In science, the word fission means to split, so nuclear fission means to split the nucleus. In the same way that chemical bonds between atoms within molecules store chemical potential energy, the bonds inside the nuclei of atoms store nuclear potential energy. When chemical bonds are broken, chemical potential energy is released, and when bonds within the nucleus are broken, nuclear potential energy is released.
Nuclear potential energy can be released from any nucleus, but it's easier to release nuclear potential energy from some nuclei than from others, and some nuclei give a larger amount of energy per fission than others. The heavier the nucleus, the more energy is liberated per nucleon.
The nuclei that are used in nuclear power stations are chosen not because of the amount of energy they release in fission processes, but rather because they are fissile. Fissile isotopes can maintain a nuclear chain reaction and are distinct from fissionable isotopes, which are simply those that can be made to undergo fission.
The two most important fissile isotopes are uranium-235 and plutonium-239. Both of these isotopes have been used in nuclear power stations and in nuclear weapons, and although the way in which they're used differs, the underlying principle is very much the same.
All nuclear chain reactions begin with a neutron. Usually this is a slow-speed neutron called a thermal neutron because it moves at the same speed as air particles at room temperature. This neutron strikes a nucleus of uranium-235 or plutonium-239 and creates either uranium-236 or plutonium-240. These nuclei are unstable, and this causes them to very quickly split or fission. When these nuclei split, they form fission fragments, with one usually about a third of the original mass and one with about two-thirds of the original mass. These fragments fly off at high speed, and it's their kinetic energy that constitutes most of the energy released in a nuclear fission reaction. It's these fragments that form radioactive waste.
As well as releasing energy in the form of the kinetic energy of the fission fragments and as radioactive decay products like alpha and beta particles and gamma rays, the fission process also releases neutrons. These neutrons, if slowed down enough, can go on to cause further fissions, which is how a chain reaction begins. In the fission of uranium-235, an average of 2.4 neutrons is produced, and in the case of plutonium, it's an average of 2.9 neutrons. If more than one neutron is produced per fission, then a nuclear chain reaction will run out of control, and a nuclear explosion will result. In nuclear power stations, control rods are used to soak up these excess neutrons, though the reaction in a nuclear power station could never run out of control as in a nuclear explosion, because only a small percentage of the uranium fuel is in the fissile uranium-235 isotope. The remainder is in the non-fissile uranium-238 isotope. The process of uranium enrichment increases the percentage of the fissile isotope relative to the non-fissile one.